Welcome everyone, and thank you for joining us for episode 37 in the Gleeble webinar series. My name is Dan Quigley with DSI, and it's my pleasure to be your host today. Today's webinar will be a bit different than previous sessions. Today we'll be highlighting several new features that expand on the capabilities of the Gleeble platform, and I've asked a couple of my colleagues to join me. Dr. Brian Allen, DSI's Chief Metallurgist, will present our new cryogenic testing system, and Brian Martin will share information about new anvil material that allows compression testing at even higher temperatures and why that's important. Brian Martin will also share recent work developing procedures to test non-conductive materials, which is an area that we see a lot of interest, particularly in applications where high performance is necessary. And these developments have really expanded what can be done in the Gleeble by pushing the envelope in both temperature directions, low temp and high temp, then expanding the types of materials that can be tested. So we're really excited about those. In many ways, the Gleeble is like an open source platform that allows researchers to develop new testing methods or time-saving features. Today we're going to hear from a company that worked with researchers in Poland to create a sample manipulator to help load compression specimens accurately and quickly in the Hydrawedge. And we thought the Gleeble community would find this interesting, so we asked the team that developed the tool to present here today. As always, it's our goal to keep the webinar to 1 hour or less. And as we've done in the past, today's presenters have pre-recorded their presentations. However, they are here with us in the webinar and are available to answer questions during the session using the chat feature in the webinar software. So if you have a question, go ahead and type it into the chat, and the team will be able to respond either by typing a response, or if we have some time, we'll have time for some live Q&A at the end of the session. Video of this presentation will be available online soon. You'll be able to find a link to this video as well as videos of past webinars by going to our website at gleeble.com and then clicking on the resources link in the top navigation bar and then on webinars. And there you can view past webinars or sign up for future webinars. Our next webinar will be in 2 weeks, and there'll be a link up there shortly so you can sign up for that as well. But without further delay, it's my pleasure to turn this over to Dr. Brian Allen to kick us off by sharing information about our new cryogenic quenching feature.
Thank you, Dan. I would like to use the next 10 minutes or so to discuss our new cryogenic quench system that allows Gleeble users to do studies at temperatures down to minus 150 degrees centigrade. There are many reasons why researchers might want to study materials at these low temperatures, one of which is simply either use or fabrication in Arctic or low temperature environments, and another is cycling between extreme high and low temperatures, such as might occur in for instance, a rocket engine on an orbiting satellite that has to fire periodically and therefore cycles between the temperatures of the rocket flame and the low temperatures of space. Some of the other applications that we envision for cryogenic quenching is the determination of material properties at low temperatures, the development of cryogenic treatments to manage retained austenite in highly alloyed tool steels, the determination of austenite stability in trip or quench and partition type retained austenite steels, where the austenite stability is not only going to be critical for the initial forming of those steels, but also for any potential crash worthiness in an automotive application that those steels may be applied to. The studies of thermal fatigue and shock cycling of materials is also going to be quite critical, and simulation of welding or additive manufacturing in very cold environments such as Arctic or space. The cryogenic quench system that has been designed mounts to the back of an existing Gleeble onto the back vacuum tank door, and the cryogenic fluids are routed into the main vacuum tank through a series of cryogenic hoses that are routed through the vacuum tank. There are a couple of methods that we can use to apply this cryogenic quenching fluid to the sample. The primary one is the internal ISO-Q quenching. I'll discuss that a little bit later, but I think most Gleeble users are probably familiar with ISO-Q quenching. And then the other is, of course, simply an external gas spray quench, where we have a cryogenically cooled inert gas such as nitrogen or argon that we can introduce onto the sample using just an external spray nozzle. For those of you that are not familiar with DSI's cryo-quench method, it's basically a system that we've designed that introduces cryogenic fluid, or just quench fluid, into the ends of a hollow-ended sample from both sides. What this allows us to do is leave the center section of the sample solid and get very high cooling rates, while still being able to maintain an isothermal plane in the center of this section. Very useful for dilatometry or other type of material studies. Using the cryo-quench system on the ISOQ setup, it's very easy to program very complex thermal cycles both above and below room temperature, and essentially simulate any process that you may wish to simulate. This example here just shows a sample being held at basically room temperature while the cryogenic lines are cooled, heated at 45 degrees C per second up to 1100 C, cryogenically quenched down to minus 150 C, brought back up to a intermediate cryogenic temperature, requenched cryogenically, and then brought back to room temperature. This is not really a heating or cooling cycle that represents any specific process, but simply an example that we've used to show the versatility of the cryogenic quench system and how it can be programmed for any quench rates, heating rates, and how it can be used to simulate any process that you may need to simulate. The minimum specified temperature of this system is minus 150 degrees C. It's probably possible to go a few degrees colder than that using liquid nitrogen, but we've been pretty conservative with our specification at minus 150 degrees C. I will point out that the average cooling rate is not that fast. We do get a lot of customers that have questions about cooling with liquid nitrogen, and they're looking for liquid nitrogen not for cryogenic temperatures but for faster cooling rates. And unfortunately, liquid nitrogen does not really give a faster cooling rate than water. And this is due to a couple of reasons, primarily the Leidenfrost effect, or the barrier layer that occurs when you try to quench a sample with liquid nitrogen, and also the fact that liquid nitrogen has a much lower heat of vaporization than water does. So for temperatures above the boiling point of water, water is actually probably a faster quenchant, but obviously you can only get down to 100 C, at a very fast rate using water as a quenchant. Of course, the cooling rate does vary with the temperature of the sample, and this table here simply shows how that cooling rate changes. At higher temperatures, between 1000 C and 600 C, we get about 60 degrees per second in the ISOQ setup, and that falls off to that 10 C per second I talked about before as we reach those room temperature down to cryogenic temperature ranges. One thing I would like to point out too is that for our system, there are no expensive and difficult to maintain cryogenic pumps or other equipment that's required. We simply use the vapor pressure from a readily available Dewar system to push the liquid nitrogen temperature out at about 22 psi, which is more than sufficient to get these cooling rates that we're talking about here using the ISOQ setup. Previous slide, I'll go back to it here just for a second, is that you can see the transition that occurs in a steel sample as we go from the austenite to ferrite regime. And if we plot that same data on a instantaneous cooling rate curve, we can actually see quite clearly the transformation temperatures that occur in this material. So we have not yet explored using this for any kind of a dilatometry type of work, but it is just an interesting aside that I thought might be interesting to point out for the group. This is just a slide that talks about just the dynamic nature of this. So we do have the ability to heat and cool and reheat. So we can do high temperature to cryo cycles at any heating and cooling rate with any degree of hold time, either on the hot side or the cold side, that may be necessary for the studies that you're doing. Or we can cryogenically quench between different cryogenic temperatures. On the right, you see a plot of a sawtooth wave between minus 100 and minus 150 C over the time spans illustrated. So the takeaway from this slide is that the system has quite a bit of flexibility, and you can really program in essentially any heat cycle that you want within the heating and cooling limits of the Gleeble itself and the cryogenic system. The cryogenic system itself includes the full turnkey solution that can be just added to any existing Gleeble, including the liquid nitrogen Dewar to collect any waste liquid nitrogen, the dynamic control software, and all the piping, tubing required to both use this in the ISOQ and or the direct quench configuration. You do have to have one of our new Gleeble Touch consoles in order to utilize the cryo quench. The system does not actually come with the liquid nitrogen supply tank. This is because most researchers buy liquid nitrogen from a gas supplier and it comes delivered in the dewar. So typically, similar to high pressure bottled gas, usually the liquid nitrogen supply tank is supplied by your liquid nitrogen supplier. So that is also different in every location of the world. So we can certainly work with you if you need to get a supply tank, but the supply tank is not included with the base package. So moving on a little bit, I've been talking so far about mostly the ISOQ integrated setup. We also have the ability to use cryogenically cooled gas to quench the sample directly. So this simply shows a picture of a Gleeble jaw with a quench head installed, and this is actually nitrogen gas that has been cooled through a liquid nitrogen bath, and it is being sprayed into the Gleeble. Now there is no sample in this demonstration photo, so the Gleeble sample would sit right here. The reason that you can actually see these gas plumes is because this is done just in open air, so we're actually getting some condensation on this liquid nitrogen. Now, was this done inside the vacuum tank after a vacuum had been pulled, you would have no condensation and you would not be able to see this cold nitrogen gas flowing through this nozzle. But this just shows a good illustration of the gas pattern. And of course, these nozzles are adjustable to get whatever gas flow pattern you would like to have. And then on the right, we show the cooling rates achievable for a couple of different nitrogen gas pressures. And again, we are controlling this nitrogen gas flow with our gas controlled quench, so we can control this up or down and get whatever cooling rate may be necessary. One of the things with the external quench, of course, is that you have to realize that you will develop a very significant thermal gradient. As you're only quenching the outside of the sample, the inside will be still hot, so depending on the thermal conductivity of your sample, the gradient will be you will introduce a gradient depending on the size and conductivity of your sample. The external cryo quenching performance, this is done on I believe a 10 millimeter sample, and just shows the cooling rates from different temperature ranges. So again, fairly fast cooling rates at the higher temperatures, and then once we get down to room temperature to minus 60 degrees or so, fairly slower cooling rates of about 6 degrees per second. So I'd like to thank you all for your attention. As always, we are available to answer any questions or provide any clarifications that you may need. So back to you, Dan. Thank you.
Thank you, Brian, for putting together that presentation and sharing this new capability with the Gleeble community. We are interested in hearing feedback from the community on this, so Brian has listed several applications for cryogenic testing, but we want to hear from you. So please use the chat tool. Let us know if you are interested in this type of testing and how you're seeing it fit into your research. That feedback is always really important to us. Up next is Brian Martin. Brian joined DSI a couple of years ago after studying at Iowa State, where he was able to use the Gleeble in his research. Brian Martin and Brian Allen both head up DSI's contract testing team, where they work with researchers that may not have access to a Gleeble. So if you contact us about conducting Gleeble tests for you, you'll likely end up working closely with both of the Brians. As I mentioned before, Brian will be presenting examples of testing for non-conductive materials, as well as share information about new anvil materials that allow for compression testing at even higher temperatures. I'll turn this over to Brian.
Good morning. Thank you all for being here. My name is Brian Martin, Gleeble Applications and Testing Engineer here at Dynamic Systems. I'm going to be presenting today on some recent new options that have been developed for the Gleeble system and how they can expand the capabilities of Gleeble testing. The first item on the agenda is some new ultra-high temperature compression anvils for use in our uniaxial compression test setup. Here's an outline of this section. First, we're going to do an overview of some of the ways that the uniaxial compression test is used, followed by the limits of our current standard setup. Finally, I'll review work that we've done to validate these new ultra-high temperature anvil materials, and the future applications of this setup. Uniaxial compression testing is one of the most widely used Gleeble tests. A cylindrical sample is held between electrically conductive anvils, heated to temperature with the Gleeble's direct resistance heating, and deformed at any number of thermomechanical cycles. The anvils are made of sintered tungsten carbide, which is both electrically conductive and thermally insulative. This allows for direct resistance heating while also keeping the material relatively thermally isolated to impose a uniform temperature across the specimen, hence the shorthand ISO-T for isothermal anvils. The setup was primarily developed as a single or multi-hit forging simulation, and this remains a large part of its utility. But the stress-strain compressive data can also be used to feed into numerical simulations to develop constitutive equations of the alloy in question for application to any number of hot working processes. In addition to the aforementioned process simulations, this can of course also be applied to getting material properties at temperature, things like elastic modulus and yield strength. Control variables of the uniaxial compression test are identical to the relevant processing variables found in a steel mill, namely temperature, strain rate, as well as final strain. So shown here is an example of some work that's been done on a Gleeble to generate these so-called hot working or processing maps for specific alloys, in this case a high alloy steel. Multiple compression tests are run across several strain rates, temperatures, and final strains, and based on the stress-strain response, a workability map is generated. This diagram shows which regions will result in cracking, non-uniform flow, which you don't want to be operating in your steel mill, as well as the strain rate temperature regions where the material can be hot worked with no issues. These hot working diagrams are a very useful graphical representation, I feel, to visualize the complex mechanisms at play during uniaxial compression and hot working. They're invaluable to understanding how best to create parts through hot working. And you'll see that in a lot of these diagrams there is a limit as to how high the temperature goes, how high we can operate in generating these types of data. Shown here is another very good example showing these process maps generated from Gleeble work, in this case on Inconel's 625 nickel-based super alloy. The micrographs here also show, the complex, multifaceted microstructural processes going on at different temperature and strain rates. At too low of a temperature and too high of a strain rate, we don't get any dynamic recrystallization, and an accumulation of deformation and strength would eventually lead to cracking at higher strain values. Conversely, at too high of a temperature but too low of a rate, we get unwanted grain growth, and complete dynamic recrystallization is only found at elevated temperatures and high strain rates. Once again, we're only looking at a narrow window in terms of both the strain rate space and the working temperature space. For some of these, more standard run-of-the-mill alloys, that might be perfectly viable, but there could be reasons why we would want to go to higher temperatures. The application of these processing maps, as well as uniaxial compression testing and other hot working simulation options on the Gleeble to full-scale industrial rolling mills, should be pretty evident. If we have a better understanding of how the material will behave under hot working conditions, we can more efficiently process them. Savings of time and money, for example, can be achieved by fewer passes with higher deformation during each pass, which might require higher strain rates, in which a higher temperature hot working may be the answer. The uniaxial compression test is also frequently used in the Hydrawedge system, in which multi-hit forging and rolling at very high strain rates can also be directly simulated. So now that we've gone through some of the applications of the uniaxial compression testing towards simulating the hot working process, we can understand how exploring higher temperatures for hot working might be the next logical step. Processing of existing alloys can be made more efficient through higher strain rates, lower loads on the tooling, and fewer total passes. But I think more crucially and more interestingly, the processing of new higher temperature materials will require the development of new processing methods. So here is sort of a qualitative diagram of the temperature regions of an example low alloy steel. In addition to understanding properties of materials at higher temperature. So right now, many of our users are already at the temperature limit of the Gleeble system, especially when applying it to commercially useful nickel and titanium alloys. New breeds of even higher temperature materials will require even higher temperature working conditions, especially for critical areas such as aerospace and energy applications. So this, I think, is a kind of a good visualization of the type of engineering that we're interested in, where the temperature ranges of our materials increase each year. Shown here as an example of the increase in operating temperatures of turbine blades in jet engines since the 1940s, starting with uncooled nickel-based superalloys into actively cooled turbines made from highly engineered single crystalline growth cast alloys and thermal barrier coatings. This brings us to the solutions we're working on to extend the temperature ranges of the Gleeble system. For those unaware, our compression anvil is an assembly of multiple parts with an anvil base and an anvil cap that's held in direct contact with the specimen. Between these two are a series of variable graphite discs used to adjust the electrical and thermal resistance of the anvil assembly. Historically, the setup has had an absolute upper limit of 1400 Celsius, although this is highly dependent on the loads experienced by the anvils, the hold times, as well as the number of cycles that the anvil assembly is expected to last. The binder used in our tungsten carbide tooling begins to break down, the anvil caps get soft and start to indent, strain data becomes questionable, and finally the anvil caps will eventually fail. Slightly higher temperatures can be achieved. We can get to that 1400 Celsius through the use of pure tungsten anvils, although those also have their issues related to brittleness and higher thermal conductivity compared to the carbide. As a solution to this, we've begun testing and working with new ultra-high temperature anvil caps, which have had successful runs up to 1900 Celsius. Preliminary testing started by simply replacing the anvil cap of the standard anvil assembly with the new high temperature cap. We use C-type thermocouples, the tungsten rhenium based thermocouples, peened into a molybdenum alloy specimen. Tests are run at 100 degrees Celsius increments from 1300 degrees to 1900 degrees Celsius. Shown here are both the time temperature plots of these aforementioned tests, as well as the stress strain data generated from these ultra high temperature tests. Each test was followed by careful examination of the anvil caps for cracking, indentation, any sort of thermal breakdown, and they looked frankly perfect even after multiple tests at very high temperatures. However, after the final tests, it was noticed that the anvil bases themselves had been deforming. The tungsten carbide anvil bases were still getting much too hot for them to perform well. Shown here on the left are the bases after those multiple tests up to 1900 Celsius. The anvil caps themselves are shown there for reference. They were totally undamaged and not welded to the bases or anything like that. And on the right are the bases, again, after a single test at 1600 Celsius. Even after one test, they show significant deformation. So we switched to running tests with pure tungsten as the anvil base. As I mentioned, it has a higher thermal conductivity than the tungsten carbide, meaning it probably saw much lower temperatures than the tungsten carbide bases saw, as well as having just better stiffness at temperature overall. Several tests were again run up to 2000 Celsius, and the anvils and anvil bases were no worse for wear. On the other hand, some of the other parts of the setup melted at these temperatures, so I think 2000 Celsius is going to be our current limit for this new ultra high temperature anvil material. Wrapping things up here, hot working simulation is one of the key pieces of the Gleeble suite of capabilities. Hot deformation will always be a critical part of the Gleeble system, and DSI will continue to work on the cutting edge of material research. As technology moves to develop even higher temperature materials and then eventually move them into commercial applications, the hot working of these materials will be a key part. The introduction of these high temperature anvils have once again pushed the temperature capabilities of our uniaxial compression testing setup up to 1900 degrees Celsius. We have worked with and will continue to work with industry and university partners to roll out these anvils. So we're already working with real world applications for these much higher temperature capabilities. Running tests on some refractory materials, high entropy alloys, as well as refractory high entropy alloys up to 1700 degrees Celsius. Now we're shifting to a very different type of new capabilities for the Gleeble system. That is the heating and testing of non-conductive materials. So we'll start here with a brief reminder of the current heating capabilities of the Gleeble system, followed by some applications of our resistive and our inductive heated systems and how they're used to indirectly heat non-conductive materials. Historically, the resistive heating capabilities of the Gleeble have been the foundation of our ability to simulate metallurgical processes, and this direct resistance remains the primary focus of the Gleeble system. However, we also pride ourselves on flexibility in test configuration, and in recent years, DSI has added inductive heating capabilities to our suite of options. In certain applications, especially where uniform heating in the axial direction is of critical importance, induction can have advantages not found with direct resistance. However, both of these methods rely on joule heating to directly heat metallic samples, which has always been the focus of the Gleeble system. But thermomechanical testing of non-conductive materials is also of interest to many of our customers, and the development of an option to indirectly heat these non-conductive materials has made significant progress over the past year. Our first prototype was a simple add-on to the standard pocket jaws, still using direct resistance. A metal tube susceptor is mounted to one side of the jaws, with current carried by cables attached to either side. Shown here is both the 3D model of the engineered concept as well as photos of the prototype. Here are a few more pictures of the system, both during heating and afterwards, showing the red hot tube heating a ceramic specimen. We were able to get the temperatures up to 1200 Celsius, but having the tube coupled directly to one of the jaws made loading the sample rather difficult. Centering the thermal gradient was also a challenge, as the side that the tube was attached to was cooled much more than the free side. There were also problems with the tube itself bending and breaking at temperature, although the material designed for higher temperature service may be able to extend the capabilities and make this a more viable option. So given the challenges with a direct resistance heated setup, we started to look at the inductive susceptor method as an option. This setup in many ways was much simpler, as the induction coil is completely decoupled from the mechanical system, meaning that thermal and mechanical control can be operated much more independently. There's also no contact between the susceptor itself and the actively cooled Gleeble jaws, meaning that heating is much more efficient and thermally uniform. The configuration we've chosen consists of a graphite tube surrounded by ceramic shielding and held within the induction coil. The ceramic serves to both electrically isolate the conductive graphite from the coil, as well as provide thermal insulation to get efficient uniform heating through the length of the tube. Temperature control is achieved with thermocouple wire junctions held in the tube, effectively mimicking a tube furnace in the Gleeble vacuum chamber. So shown here are some of the first results that we've generated, showing good thermal uniformity, rapid heating, as well as the ability to effectively hold at elevated temperature. So the idea of an inductively heated graphite susceptor being used to heat non-conductive materials is certainly nothing new. As I just mentioned, there are several attractive advantages to a graphite inductive susceptor, which can be credited to its longevity. In addition to independent thermal and mechanical control, the graphite itself is relatively cheap and easily machined, and can be heated up to 3,000 degrees Celsius in a non-oxidizing environment. Shown here are a few models of some of the most recent iterations of this design. A tight-fitting slot machined to a specific sample geometry was found to be a critical piece of the design puzzle. It results in much more uniform heating with much better control and a greater degree of confidence that the ambient temperature within the graphite tube is the temperature that the sample itself is experiencing. As many of these materials that can be tested cannot be measured directly with a thermocouple junction. At a reduced section gauge length also helps to ensure that the area deforming is at an isothermal condition. Here's another 3D rendering of our most recent setup, showing the induction coil holding our graphite susceptor assembly in the center of a specimen. The whole situation is mounted in our low force jaw carrier kit, and the sample itself is held in some custom designed grips to hold these non-conductive samples. So we have pushed the temperature limit of our current setup. The aluminum shield does indeed start to melt as we get close to 2000 Celsius. So right now we're only able to get to temperatures well below that. But we have yet to hit the limit, even with very high heating rates and extreme temperatures, of our inductive power supply. So theoretically, we should be able to get to higher temperatures, provided we can find higher temperature materials that will serve as good thermal and electrical insulators for this system. So where does that leave us? Thermomechanical testing of non-conductive material will always be of interest to our customers. And having a Gleeble add-on that can provide a solution is something we've put real effort into and has certainly provided us with promising results. This first pass at integrating an inductive susceptor has hopefully demonstrated the viability of such testing. Even though there's still work to be done, all we've done so far as mechanical testing has been uniaxial tension testing in both constant strain rate and constant force. And regarding the thermal capabilities of the system, we are currently limited by our tooling to temperatures below 1900 Celsius. So with that, I'd like to thank you all for your time, and I hope we have the opportunity to help you out with your research with these new technologies that we've developed.
Thank you, Brian. Great job sharing some interesting new developments with the group. As a reminder, if you have questions for our team, please feel to reach out to us directly. Our team loves a good challenge, and we always enjoy working on new projects. And speaking of new projects, our next presenters developed a custom tool for the Gleeble Hydrawedge for some of our Gleeble users in Poland that were looking for a faster and more accurate method to load specimens in the Hydrawedge. Sandra, Spinkiewicz and Radoslaw Szlarek from Spinex will be sharing more information about their specimen manipulator. They have pre-recorded the following video, and it's complete with some nice animations, so we hope you enjoy.
Thank you guys, thank you so much. Greetings from Poland. Let us introduce ourselves. My name is Sandra Spinkiewicz, I'm the owner of the company Spinex.
And my name is Radoslaw Szlarek, I'm a project engineer.
Let us show you something interesting. Perhaps you are wondering what a company from Poland is going to present today. This is what we want to get your interest in. The new optional sample manipulator for Gleeble Hydrawedge 1 and 2. Working fine with both types of the machine. Just a few words about Spinex. We are a trade company experienced in refractory metals, hard materials and also special glues and valves for food industry. Since 2013 we have also an R&D department where we research, develop and deploy new materials for many industries. Our motto, which we have borrowed from Professor Jan Kaczmarek, a former Polish Minister of Science and Higher Education. Science is responsible for discovering everything which physically exists. Engineering is responsible for making things which have never existed. To give you some background of the project, we want you to know why we have developed and manufactured the sample manipulator. We did it because Gleeble Hydrawedge users asked us to do it. And we love to bring solutions, especially that it was an interesting problem and it was for us also a challenge to find the right solution. Why have Gleeble Hydrawedge users asked us to take a look on sample positioning? Maybe because they thought that the specimen positioning takes a little too much time and requires an additional tool. Maybe to ensure that the positioning process is as precise and as easy as possible. And for us, it was an interesting challenge in which we wanted to construct a high quality and durable positioner, which allows you to reduce the time which is needed for sample positioning, make the process easier and more precise. We had to face several challenges, which were mostly the limited space inside the Hydrawedge chamber, the high temperature and the unstable environment inside the chamber. Also, we wanted to adapt our positioner to the existing chamber construction. Now I will pass my voice to Radosław, who will bring you to the technical details.
Thank you, Sandra. My name is Radosław Szlarek, and I would like to tell you about our sample manipulator. Our product lets you move the tested sample between the anvils before it will be blacked. The centering process is simple. Just turn dedicated knobs for moving left-right and up-down as well. The center position is corrected by eye. We plan to improve it in future by using a special optical and mechanical kit which could upgrade our present manipulator. This is a comparison of two solutions. Standard, marked as red, you use it now. And our new proposal, marked as white. You can also see the big size difference between these two hardware. Simply moving the sample in two axes needs a much more complicated design. And this is front view. As you see, a loader is installed on our manipulator. In this photo, you see a present solution from DSI dedicated to Hydrawedge 1. And another photo. It is a standard installation kit for loader and lets you change the position of the sample between the anvils. This is the same solution from DSI dedicated to Hydrawedge 2. And this is another photo. Present solutions from DSI, which are dedicated for Hydrawedge 1 and 2, are known. It requires some time, special tools, and patience to centric the sample between the anvils. What do we offer for you? An option which lets you do the same faster with no additional tools. Now you have two options for centering the specimens between anvils. First is a standard solution from DSI, which you know. It works well, but we offer you something more. You will save your time and improve your efficiency during the science tests. And now this is time for this. Let's watch how you can install and use our manipulator. It may also work for you. And this movie shows you how our manipulator should be installed and how it works in practice. This is chamber of Hydrawedge 2. As you see, loader is installed onto a standard DSI solution. First, you have to remove the loader. Just twist off the screws and uninstall it. Remember about disconnecting the power cable for solenoid. Now you can uninstall the standard DSI kit. Twist off the inbus type screws. These screws must be also twisted on and off during the standard sample positioning process based on the DSI kit. You know how much time it takes. Grip Hydrawedge 2 is ready for new sample manipulator installation. Let's install it. This process is disposable. You do not have to uninstall the manipulator. You can move it out of course to a cleaning routine process, for example, or something like that. First, twist on the right inbus type screw. Then move the manipulator position to the right by turning its right knob. Now you can twist on the second screw. manipulator is ready for loader installation. Install the loader on the manipulator. Just use the same screws to twist it on. Don't forget about solenoid connection. It must be on. Another step is the installation of the steel cover bar, which works as water protection. This cover bar is a standard Hydrawedge equipment and installed on the chamber's door. If this cover bar is installed, you can't use our manipulator with Hydrawedge. It is impossible to close the chamber's door then. Hydrawedge can operate without this cover bar, but it will not be necessary. We will add a steel cover bar which replaces the standard DSI bar and is adapted to manipulator installation. We can use the manipulator and loader now. Move the loader's arm, which holds the sample, to the tested area between the anvils. Set the required position for the anvils by changing stroke and wedge parameters. Next, turn manipulator's knobs for centering the sample. Two vertical knobs are used for up-down moving and horizontal knob for left and right. Two vertical knobs guarantee better stabilization of the loader and the sample. The final position is corrected by eye. The simple way for centering the sample is moving it to the middle of the left anvil. When it is done, just move the right anvil by changing the wedge position. Left and right anvils are in the same line, so the center position is the same for both. You can make small corrections of sample position at the end. Now you can start the process. This is our manipulator installed inside the chamber of Hydrawedge 1. Loader is ready for working. And installed inside the chamber of Hydrawedge 2. Loader is ready for working as well. Manipulator was successfully tested for a few years by two Gleeble users in Poland. Thanks to it, we improved its design, and now we are ready for sell you the complete final product. Very important thing during manipulator installation is the steel cover bar, which is standard installed on the chamber's door. It must be removed and replaced by a stainless steel replacement added by us to every order. Inside the Hydrawedge chamber is very low space, so every centimeter or inch square is needed. Sample manipulator was designed and produced in Poland. We used high-quality materials for its manufacturing. We will produce it in Poland in future also, and take care about its service and replace parts. You will be sure that every manipulator and its every part is very high quality. Our company was established 31 years ago. We guarantee that you will be in the right hands. Thank you for your attention.
So once again, thank you very much for giving us the opportunity to present our manipulator today. Once we've got your interest, please don't hesitate to contact us.